Yeah, this some of this data is a couple of years old now, but I realize it hasn't actually been presented at EGP yet under sources. And so we have some new work that we results that we that Samrat, my postdoc, has generated over the past couple of years. But most of the data I'll be showing now was generated a few years ago. So I'll be showing work on fingerprinting sources of polycyclic aromatic compounds, PACs, in the Athabasca oil sands region using compound-specific isotope analysis. And so these are the three main players that are involved in this project. And yeah, so what are PACs? There are large, you've seen some data on PACs in the various talks previously, but just to summarize, PACs are a large group of ubiquitous organic contaminants containing thousands of individual compounds. They include, but are not limited to, polycyclic aromatic hydrocarbons, PAHs, alkylated PAHs, which contain one or more methyl groups, heterocyclic compounds with one or more nitrogen, sulfur, or oxygen atoms in the aromatic ring, and oxygenated oxy or nitrogenated PAHs. And so they're found naturally in petrogenic sources, such as crude oil and coal. And they're also formed from incomplete combustion of organic matter. And that's the term we use for that is pyrogenic, and also through diagenetic processes. So they have a wide variety of sources, and they're toxic to a known range of wildlife, and of course, including humans. And so just to visualize these are what PACs look like. And so here you have, classic PAHs, including some of the 16 EPA priority PAHs on the left, alkylated PAHs containing methyl groups, sulfur, nitrogen, and oxygen containing PACs. And so PACs, in the context of environmental research in the oil sands, various studies carried out over the past decade have shown an increase in PACs to lakes in the Athabasca oil sands region. And so here's a study carried out by Kurek et al. 2019 that was published in Proceedings of the National Academy of Science. You can see here that starting at around in the 70s, during the modern increase in production, exploitation of the oil sands, you see a dramatic increase in the total PAHs over the last couple of decades. And so in the Lake NE20, right in the center of the oil sands region there. And so work we carried out under CORS a while back with my PhD student at the time, Josue Jadzi. And we also saw an increase in PAHs in a lake further away, about 50 kilometers away from the heart of the operations. And so we attributed this to dust, but there's a wide variety of potential sources. Dust from unprocessed oil sand. That was what we thought it was, using carbon-13 values. But there's a wide variety of potential sources. Atmospheric sources are the ones I'm talking about in this presentation. So you have wildfires, you have unprocessed oil sand dust, which I mentioned was a potential source considered for that Athabasca, Alberta Lake E. You have pet coke. So pet coke is the carbonaceous byproduct of bitumen production, which they store in these large piles in the oil sands region. Right there, you can see the picture of that. Then you have vehicle soot from the large trucks and diggers they use in the extraction processes, plus just trucks from the highways around the region. And less relevant to atmospheric airborne inputs is bank erosion of natural bitumen outcrops. So the question is, in terms of from an environmental management perspective and a government of Alberta perspective, how can we identify and potentially quantify different sources? This is very important to understand potential negative effects to the environment in the oil sands region. So of course, what we've done over the past decade is using compound-specific isotope analysis. So think of this as a fingerprint, for example. So especially when you have two isotopes, you can combine carbon and hydrogen isotopes on PAHs, PACs. As long as you understand the variability in the source end members you're analyzing, and you've you can assess the potential end members into your system, you can use these values to do a mass balance and quantify your sources. So here's an example of one PAC. The one that's relatively easy to analyze in our extracts often is phenanthrene, 3-ring pH. And so you can see here, you have fantastic separation between most of the main sources in the oil sands region. So how do you measure carbon-13 values and deuterium values on pHs, PACs? Well, you do it by gas chromatography, isotope ratio mass spectrometry. So you separate your compounds, after doing various cleanup steps to get your extract that's in a solvent to the point where you can separate your peaks well. And in terms of carbon, for example, you combust your peak after it dilutes from your gas chromatograph. It's combusted in your isolink system at 1050 degrees Celsius. And then you measure the ratio, you ionize your CO2 in the ion source, and then it's accelerated down a flight tube, and the masses are deflected on a magnet into fixed collectors where you measure mass 44, 45, 46. And after doing some corrections, you can get a carbon-13 value of individual PACs, peaks. And the same thing for hydrogen. Of course, you have different collectors set up for hydrogen and pyrolyze at 1450 degrees Celsius. So in the context of previous work and trying to better understand the sources of PACs deposited to lakes, which can be quite high in some of the lakes within close to the geographic center of oil sands operations, we carried out some work in snow that was collected from the surface of frozen lakes in the Athabasca oil sands region. So here you can see in the center there, AR6, that's typically used by people working in the oil sands region as a geographic reference point for the heart of the oil sands region. And you can see it's about 50 kilometers north of the city of Fort McMurray. And just by coincidence, this study took place the winter following the large 2016 Fort McMurray wildfire that took place May the previous year. So we had an opportunity to measure, potential inputs from ash that was due to the previous year's forest fire, or to assess the impact of that in the snow on these lakes in the following winter. So these graphs show the particulate loadings and the total PAC loadings in the snowpack. And so plotted versus distance from AR6 on the x-axis, you can see that you have a substantial drop-off. So the 4 lakes, or especially the 2 lakes NE13 and NE20, situated very close to the operations, have very high PAC loadings and very high particulate loadings in the snowpack. And that drops off the further away you get from that reference point. So the reference point has its limitations, but it's still very useful for doing these atmospheric loading plots. So looking at the isotope data. So compound-specific values of phenanthrene on the left graph, and in an alkylated phenanthrene on the graph on the right. And the dashed lines on the graphs correspond to the end members, which I showed beforehand on the bi-hydrogen carbon plot. So you can see here that the values of phenanthrene and C1 phenanthrene in the lakes closest to the operations, like NE13 and 20, correspond to values that are close to the end member of petcoke and to unprocessed oil sand. And that's and you can see you can kind of eliminate gasoline diesel soot as a source. And in the lakes further afield, it appears that forest fires, from what we measured in the ash from the 2016 forest fire, become a more important source. So we weren't able to get as many data points with hydrogen just because of the mass constraints. You need a lot more mass of material to analyze hydrogen isotopes and pHs. But we were able to get the values in 4 samples that had the highest pH concentrations, and in a combined sample that represented the lakes that were within the heart of the forest fire area. And so you can see here that I just, the hydrogen values are different. They plot differently than the carbon values, but you can see here, you show the lakes I mentioned beforehand that showed a potential oil sand or petcoke signal are showing predominantly petcoke signature here using the hydrogen isotope values. And in the previous graph, we could discount gasoline and diesel soot as a source. So that basically points, by looking at that qualitatively, to petcoke as being the dominant signal. And so now you can quantify that in an isotope mixing model. And so here we have those 5 lakes, or the 4 lakes plus the 5th combined lake, where we have a pretty good statistically significant understanding of the main sources of PACs to these lakes, at least phenanthrene rather, or alkylated phenanthrene. And it's indicating that petcoke is the main source, which confirms a finding we actually saw in a lake in the Athabasca Delta in the previous study, the first time we actually applied to combine carbon and hydrogen isotopes. So taking this work further, in our current project we have with Alberta Environment Parks through an SPA, and now we're looking at sources of PACs in the Athabasca River. And so SAMRAT is working very hard on this, and we're also working very hard to actually get our method so that we can actually analyze more PACs than just phenanthrene and alkylated phenanthrenes for carbon and hydrogen isotopes. And so the work on carbon is finished, and you can see here that in the Athabasca River, from sampling points M3 being upstream and X6 being downstream, the main stem of the Athabasca River, you can see that there's a much more wide variety of different potential inputs, just looking at the qualitative evidence we have now based on carbon-13 values compared to the dust. So the river is a much more dynamic system than what you're measuring in snowpack. And so the concentrations, I might add, of PACs in the river were very low too. But you can see here that for some of the higher molecular weight ring PACs like fluorantine and pyrene and BK fluorantine, you can see a much higher potential for gasoline and diesel soot input. So anyway, this is work in progress, and we're waiting to do our hydrogen isotope analysis on as many pH as possible, mass, as long as there's enough mass available. And thank you. This is everyone involved in this previous work who's contributed. And yeah, so the source of this funding was from both EGP and Alberta Environment and Parks, and from a PERD project, which we received a few years ago. Thank you.